Assalamu alaikum, my dear students. How are you? Hope you will be fine and okay. By the time you watch this lecture, you will be in the best of health, wealth, and happiness. I welcome you all into my today lecture. In our today lecture, we will study about the specific heat capacity, the heat capacity, and the application of the large value. The applications of, because there is not just one, large value of the specific heat of water, and then we will discuss the latent heat also, right? But I will only give a simple introduction to the latent heat, and I will explain the latent heat in my next lecture. Now, what is the heat capacity? Class, this is our a common observation. For example, let's say I will tell you that if you go to the park, right, and if you just see if there are two benches, one is made of iron and the other is of marble, right, stones like that, and if somebody give you the option to sit, then naturally you will choose the one that is of the marble, because in the sunshine, right, it will be less hard than the iron. Similarly, if you are sitting beside the swimming pool at the noon time or at the morning time, and then when you just check the water in the swimming pool, if it is in the open sky, then you will feel the water less warm than the surrounding, right? For example, the concrete boundaries around the swimming pool. Now, why these all happens? The answer is the specific heat. Similarly, another interesting thing is, for example, if you just see, I will tell you that if you place a spoon, steel spoon, and water in a cup, and if you place these two in the sunshine, and after 3 or 4 minutes if you visit to check, right, then definitely you will feel the spoon warmer than the water in the cup. But when you bring it to your room, and then after a while if you touch, then what you will feel that the spoon is cooler than the water in the cup now. So why these all happens? This is what the very safe experiment you can perform at your home also. The answer is what? The answer is the specific heat capacity. Now, what is the specific heat capacity? It is the amount of heat energy required So what is this? It is the amount of heat energy required which can raise the temperature of a unit mass of a substance, which can raise the temperature of a unit mass of a substance by 1 Kelvin, by 1 unit. That is known as the heat capacity. Experiment shows that the amount of heat energy required, this amount of heat energy required depends upon various factors. That is the first one. Sorry. The amount of that heat energy required, it depends on what? This is the amount of heat energy required. It depends on what? The mass of the substance. That substance, this is equation number 1. First, it depends on what? It depends on the mass of that substance. For example, if I choose two masses of the water, for example, 2 kilogram of water and 1 kilogram of water, right? And if I want to raise the temperature of the water, for example, if the water is at the temperature of 17 degrees centigrade, and if I want to raise the temperature of the water to 18 degrees centigrade, then the 2 kilogram of water will require more heat energy, rather the double, to raise the temperature by 1 degree centigrade. So it depends on the mass of the water. The second important point here is that it depends on the sector factor. The first factor is the mass. The second factor is the change of temperature. That is, depends on the change of temperature. Now, what is this delta T? This delta T equals T2 minus T1. For example, if you want to heat up the water, right? In the same, now before we have taken for this 1 kilogram of water here, and here we have taken 2 kilogram of water. So for the same 1 degree rise in the temperature of the water, for example, if it is at 17 and this is also at 17, then for the same rise in temperature, let me check. This is for the whole body, yes. Then for the same 1 degree rise in temperature, 2 kilogram of water require double heat energy than 1 kilogram of water. So that was the mass factor. Let us see the temperature factor, for example. Now, if you have the same water, the same quantity by mass, for example, look. You see here, masses are the same and both are at room temperature, but if you want the temperature of the water, for example, from 17 to 30, you want it to from 17 degrees centigrade to 25 degrees centigrade, and you want the temperature of the 2 kilogram of water from 17 to 35 degrees centigrade, then which one will require more heat energy? Experiment shows that greater the change in temperature, greater will be the required energy. So definitely to raise the temperature from 17 to 35 will require more energy than from 17 to 25. So in fact, this is T1, T2, this is T1 and this is T2. Here this is T1 and this is T2. So the greater the temperature difference, the greater will be the amount of heat energy required. The third important point here is the nature of the substance. Nature of the substance. Different substances have different heat requirement for the same unit rise in temperature. For example, if you have any other kind of liquid and if they have the same masses and if there is the same temperature as compared to any other liquid with the water, so for, let's say for example, if you have here mercury and if you have here water, so for the same rise in temperature, you see the rise in temperature is the same. For the same quantity of masses, despite these two factors the same, water will require more heat energy than the mercury for what? For the same rise in temperature. This experiment shows that the different substances have different specific heat capacity. Depends on the nature of that substance. Now let us combine these two equations into a single one. Let's see that how, as I told you, that it depends on what? The two things. What? The mass as well as the change in temperature, delta T. Delta Q equals M delta T. Now, what does this mean? This means that delta Q equals C into M delta T. Now, what is this C? This C is what? Called the constant of proportionality, and this C is known as the specific heat constant, or the specific heat capacity of the substance. And this specific heat capacity of the substance, it is given by delta Q or Q into M delta T. It can be calculated by this way. Now remember, this C, it neither depends on Q, nor it depends on mass, nor it depends on the change of temperature. It purely depends on the nature of that substance. It depends on what? It depends on the nature of that substance. Different substances have different specific heat capacity. Unfortunately, the only specific heat capacity which I remember by heart is that of the water. For the water, the specific heat capacity for water, this C is 4200 joules per kilogram per Kelvin. No other liquid has specific heat higher than the water. Water has the ability to have a higher value of specific heat constant, and then when I discuss the application, then at that point I will tell you about this. The second important point, the SI unit of the specific heat constant. Since you know that energy is measured in joule, mass is measured in kilogram, and temperature is measured in Kelvin, so it is what? Joule per kilogram per Kelvin, and the SI are joule per kilogram and per degree centigrade in other units. So you see, look at the specific heat of the water. That is, for water, if you want to raise the temperature of water by 1 Kelvin, you need how much energy? You need 4200 joule of energy. If you have 1 kilogram of water and if you want to raise the temperature by 1 Kelvin, how much energy you require? 4200 joule. And if you have 2 kilogram of water, then it will be what? 8400 joule of energy you will need just to raise the temperature by 1 Kelvin for 2 kilogram of water. So this is a very huge energy. So water has what very large specific heat capacity. For that reason, this water can be used for many ways. For example, you might have noticed that the area around the lakes or the seashore is always mild. The question is why? And the answer is very simple. It is because of the two processes. It is because of the large specific heat of water as compared to the land surrounding the water, and the process of convection. Convection we will not discuss here, inshallah, we will discuss in the next chapter. But look, you see that, for example, if this is water, lakes are like that, for example, as you see. And this is surrounded by, water is surrounded by land. This is water, right? And it is surrounded by land like this. You see, this is land, contains sands or other substances. Or now you see, look, water has a very high specific heat, right? So what will happen? Those substances which have higher specific heat, our experiment shows that it takes longer to heat up and will take longer to cool also. In those substances, like for example steel and iron, right, or concrete, which has low specific heat, it takes less time to heat and takes less time to cool too, right? Means that it quickly heat and quickly cool. And this is what the spoon and water in a cup example I already gave to you right in the beginning of this lecture. So now you see, look, they definitely water will take longer to heat up than the land surrounding the water. So what happens? The air layer near the land, it heats up quickly too, and you know that hot air always rises to the top. So when the hot air on the land surface, when it rises to the top, right, then rises above, then what will happen? It will be replaced by the cool air coming from the lakes and what the lakes or the sea, right? Why? Because it is still cool. And this is how the air currents set up. And this involves the convection also, right? That we will explain in the next chapter. But the most significant here is this one. So this is why the area near the seashore and the lakes you always find pleasant and mild. And this is why in summer you always rush to such region. So this is one of the most important example. Second, because of this, that was the first I did. The second one, the second importance of the large specific heat of the water is that it can be used as a coolant, right? To keep the heated or the hot part of usually the thermal engines at a constant temperature. So that can be used as a coolant also. For example, look at the car or the vehicle radiator. You know that the engine produces tremendous amount of heat energy, right? Along with that, excess of rather almost 60% of energy, the extra energy is in the form of what? That is in the form of heat. So the car engine need to be kept at a constant temperature, and for this purpose we use water as a coolant to keep the temperature of the car at a constant value so that the engine should not overheat and its parts should not weld together, right? Why? Because the water has a large specific heat constant and it requires a lot of heat energy for per unit rise in its temperature. So this is the reason that we use water as a coolant. The water is circulated around the engine parts, it takes heats from the engine, right, and then it's sent to a kind of storage, we call it the car radiator, and there is the fan, and the fan keep the water cool again by extracting heat from it and give it to the surrounding. And this is only possible because water has a large specific heat capacity, right? This make it the water even more useful to use it as a thermal storage. And that is, water can be used to store heat energy also, and whenever we need that heat energy, we will take it and we will use it. For example, this is most suitable in places where there is where the weather is extremely cold. At daytimes, water is stored in a large tank, and it is exposed to sunshine by some kind of mechanism and arrangement which heats the water indirectly, and then the water from that tank is then circulated in pipes into the rooms, right, where the water radiates its heat energy and keep the room at moderate temperature or keep the room warm. So it can be used for the thermal energy also. So naturally the water provide us a very pleasant, the large specific heat of the water make our weather pleasant near the seashore or the lakes, and mostly in our industry it can be used as a coolant, for example in car, or even in some places where there is excess amount of heat energy produced. It can be used as energy store also, thermal energy. So that is the applications of the large specific heat of water. The next important point here is, let me check that is the heat capacity. Heat capacity is the product of the specific heat of a substance into the mass of that substance. So the heat capacity is in fact what mass times what the specific heat of that substance, right? So it is the amount of heat energy, the heat capacity is the amount of heat energy required per unit rise in temperature, without mentioning the mass here. So definitely it is measured in joule per Kelvin here. Now what we can see here, look, that what is this? Of course MC delta T. And what is it? Delta T. So what will happen? This will get cancelled. So it is the mass times the specific heat constant of the given substance, right? So that is what? That is the heat capacity of any substance. This is very easy. There is nothing special about it, or it is not a kind of rocket science which we cannot understand. So the most conceptual part was the previous one. So if you know the mass of a substance, for example, if you want to find out the heat capacity of 30 kilogram of water, so 30 multiplied by 4200 joule, that will give you the heat capacity, right? That how much heat 30 kilogram of water can accommodate for you. Okay, so that is all about the heat capacity. And the next one is the latent heat, right? Now what is the latent heat? Latent heat is the amount of heat energy required, it is the amount of heat energy required the amount of heat energy required to change the state of unit mass of a substance. Unit mass of a substance, right? A, its freezing point, or at its boiling point. For example, if you want to change the 1 kilogram of water from its liquid state to its gaseous state, then how much energy it will require? That will be called the latent heat energy. Latent is in fact not a Greek word which means hidden. Right? Why it is hidden? Because one simple thing you know, that whenever there is addition of heat energy, whenever you add heat energy always increases the internal energy of the molecule of a substance. And if you remember my very first lecture, I told you that the increase in the internal energy will be indicated by increase in the temperature of a substance. So if the temperature of the substance increases, it means that heat energy is added to the system. But here you will see that, for example, if you want to change 1 kilogram of water into a steam, here you will see a constant supply of heat energy. And if you have the thermometer, and once the thermometer starts reading as 100 degrees centigrade, still with the addition of more heat energy to change water into steam, you wouldn't see any rise in the temperature. There is a question, why no rise in temperature? And I will answer it in the next lecture. Right? This is why it is called hidden. Why? Because it is not indicated by a thermometer. The thermometer does not show you any apparent increase in the temperature until all of the water changes into steam. Or if you want to convert solid into liquid like ice into water, right at that point the thermometer will indicate 0 degrees centigrade, and it will not show an increase even of 1 degree until all of the ice cubes melt. Right? So since there is no apparent increase during this process, that is why the term latent is used for it. So we have two kinds of latent heat energy: latent heat of fusion and the latent heat of vaporization. And both latent heats involve change of state, right? Either at the melting point or either at the boiling point. So the freezing point and the boiling point. And inshallah, in my next lecture, I will explain to you the latent heat of fusion, the latent heat of vaporization in great detail. So see you in the next lecture for this, and this is very important. Thank you very much.